So the one thing which has been really remarkable for me over the past 10 years is watching the data available to us grow exponentially. So this plot which I'm showing up here is from a very famous paper by Pierre Modal, showing the cosmic star formation rate as a function of redshift. And on this axis is telling you essentially the log of the mass of stars formed per unit time per unit volume of the universe. And on the x-axis is the redshift. And here you can see 7 points. And if you count these things, this paper might have northwards of 200 references per data point in this figure. But the point is, at this time, there were no error bars here, and we knew somewhat about up to redshift 1 and didn't know very much beyond. We knew there were galaxies out there, but didn't know so much about what they were doing. Now, if we fast forward, this is what the plot looks like now. And for clarity, I've only included data over the past 7 years and skipped some in the past year or so because we've actually gone down most recently to all the way out to redshift 12. And these are just some of the surveys and instruments which have contributed to this amazing wealth of data. And John will tell you a little bit about what's coming up in the future. But it's crazy that we can now look at galaxies redshifts 5, 6, 7, 8, 12 and tell what their star formation rates are, and then also look in the local universe from large surveys like SDSS and BOSS and use galaxies more like tracer particles of the structure of the universe, not just seeing what their properties are individually, but actually using them as probes of cosmology and other interesting, I guess, dark energy universe formation as a whole. And of course, the newest baby, DES, helped a lot by people at SLAC. And just a little bit about what we've learned from all this. There's so many things. In the first half of the universe, galaxies were growing, most of the stars were formed, galaxy efficiency was increasing, which is why you see this upward trend. And then in the last half of the universe, the fireworks have calmed down a little bit, but still there's a lot of things to be learned. And so I hope during the session today, you'll hear a little bit about many of these topics from a variety of people. So now I'll turn it over to John, who'll talk about a little bit about what the next 10 years will be about.
Okay, so Peter was talking about, Peter was telling us how far we've come in the last decade. And I think it's just going to increase the amount of data that we'll receive and observations of galaxy formation and evolution, which we'll have several talks in this session that highlight current research and open questions in this field. And I just want to go over some of the upcoming observatories that are now online. So we first have ALMA, which is now in science operation in the past year. And so this, for galaxy formation, it looks at the feel of star formation. It looks at the cold gas and dust that feeds the stars and fuels and drives galaxy formation. So I think once the science, or once the data starts coming in from ALMA, this will teach us a lot about galaxy formation all the way out until the first galaxies, out to redshift even 10. And in 5 years from now, the James Webb Space Telescope will be launched, and we'll start getting a tremendous amount of data from that in primarily the near infrared. And it has many science objectives, but one of the main science drivers of the Webb Telescope is formation and galaxy evolution itself. So, and lastly, we have LSST. So this will actually expand our knowledge of galaxy formation into the time domain and in the optical. So I think this is a very exciting prospects in observational galaxy formation. And on the theoretical side, I just want to highlight some of the advances that we might make in the next decade, primarily in the computational domain. So in the past decade or so, GPUs have been used for computational, for general purpose computing, and at first it was pretty difficult to use, and now it's getting easier and easier to actually port over your your computational domains, and so we can actually start using these without too much trouble. So I think, I mean, and also if you look at the top supercomputers in the world, the fastest ones, they actually all utilize these types of processors. So I think this is a push that we can make in an upcoming decade. And also, I think if we have crosstalk in between different subfields of computational astrophysics, we can learn a lot from each other. And to include multi-scale and multi-physics simulations, going all the way from the accretion disk of a central black hole all the way out to cosmological scales. And also, I mean, there's been a lot of talk, and first it was terascale, then petascale, and now people are talking about exascale. But I think this poses, I mean, just opens a whole can of worms, and I think it's going to be pretty difficult to actually reach this stage. There's a lot of different things that we have to look at. But I was actually Oliver Hahn and I were talking yesterday over some drinks, and we're just brainstorming how can we actually reach this. And because all of these computational tools, they have its roots 10 to 15, even 20 years ago. And we're just band-aiding these codes to actually scale up to these number of processors. But should we actually look into building a new code in this new paradigm? So I think these 6 points that I've made should provide a pretty bright outlook on both the theoretical and observational outlooks for galaxy formation. So, I mean, that concludes what I have to say, and Peter, what he has to say. So I think we'll move on to our first talk, Dan Stark. And he'll be talking about galaxy formation in the reionization era.